Okay, back again. This is part 2 of lesson 3. You were supposed to have done these 3 questions for homework, and now we're going to check and see how you did. Go ahead and mark up your papers with questions, and that way I can answer them in class when I see you. So for number 3, check your table to mine. What you had to do was plug in -2 first into this equation. So you're going to do -2 to the third power. So do you know how to do that? Let's see if we can do that. Glare. I do it like this: parentheses -2, and then there's a little caret here, and that will allow you to put into the third power. Enter. And so you get -8 when x is -2, and then you can just keep repeating that by replacing, what's the next x value? -1, so I'll put a 1 here, enter. And when x is -1, y is -1. And then you can keep replacing this number with the numbers in the data table that they gave you, and that is how I got my completed table. When you plot your points, you get that. This is maybe the second time you've seen this, but this is that S, you guys call it an S shape. It doesn't look like an S anymore, but this squiggle line like this. And that is a result of this exponent here, having x to the third. Is this a straight line? Is this function linear? No, you can tell just by looking at it. Number 4. So you have 1.5x plus 2. So we're going to just keep replacing x with the numbers that they provided in the data table. So you can see right here, 1.5. I use parentheses when I plug in numbers into my calculator. Helps me from making mistakes with the negatives. 1.5 times -4 plus 2 gives me -4. And then the next time I'm going to use -2 here, then 0, 2, and 4. And these are the numbers I got. Now, I left this for you. I almost corrected it. But I wanted you to see that I plotted my points the first time. It's actually kind of late. It is 4:54 a.m. Normally I'm doing this at 4 a.m., but I have not had any coffee. And I had a little trouble with the elf on the shelf this morning. He's very mischievous, and he made a little bit of a mess for me. So I got a late start. I plotted it. I wasn't paying attention to the scale on the y-axis. And I knew that this had to be a straight line. And when I made these dots, it kind of made this like curve. See, I was like all screwed up. So I knew right away that I made a mistake, because I know that this fits the y equals mx plus b format, where this is the slope and this is the y-intercept, and I know it's supposed to be a straight line. So knowing that allows you to catch your mistakes. So then I just replotted the points, and here's my straight line. But I wanted to share that with you because it is easy to do, but there is a way to check yourself, and the more you know, the easier it is to do that, to check yourself. So this is a linear function. Next one. You have x in the denominator, something we've never seen. It does not fit the y equals mx plus b format. So I was not expecting a straight line, and this is what we got. So you can see up top, I just did 12 divided by 1. So it's 12 divided by x. So you just keep replacing the x with whatever's here. So 12 divided by 1, 12 divided by 2, 12 divided by 3. And this was the data table I got. Obviously not a straight line. So what differences did you notice about the equations that were linear functions and those that were not? And you can pause the, oh, no, don't look at this one. My handwriting is so ridiculous. Watch, stop. I could not. Okay. My handwriting was so messy on that one. The equations that were not linear functions do not fit the y equals mx plus b format. The differences you notice about the tables, I don't know if I were you, if I would notice this, but only the linear table had a constant rate of change, and I need to show you what I mean by that. So let's go back to my other sheet. I redid this only because my handwriting was so ridiculous on the other one. Okay, and you can go back and pause that if you need to write that down, right? So when I say constant rate of change, if you look here, every time x goes up by 2, or every time y goes up by 3, x goes up by 2. Up by 3, up by 2. And you can see that this rate is staying the same. Therefore, we say constant rate of change. Now, if you go to the other tables, immediately you can see, look, the y values go up by 1 here in an interval of time, say 1 second. Then they go up by 7 in the same amount of time, if this was time. And so you can see that if this was something like the speed of something, the speed is increasing. So it is not keeping the same rate. So it does not have a constant rate of change. This is a big topic, and we'll discuss this more in class. Same here. See how the x's are going up by 1? Well, if this had a constant rate of change, you would see the same difference between the y values down here. And you can see this drops by 6. If this was to show a constant rate of change, then every interval would drop by 6. And you can see right away it's starting to decrease the speed at which it goes down. Okay, so it's not keeping the same rate, so therefore it does not have a constant rate of change. And without even graphing it, I could tell that it wasn't going to be a straight line. Okay, so there's lots of different ways there's lots of different things that will clue you in as to whether or not something's linear or nonlinear. So let's just practice together on the next page. So this is page 9. Okay, so first thing we have is the equations. And so let's look to see which ones fit the y equals mx plus b format. Well, in our y equals mx plus b format, do we have an exponent for the variable x? No, we do not. So this is going to be nonlinear because it does not fit the y equals mx plus b format. I'm not going to write it down because I'm going to try to keep the video quick. Now, this would be plus 0, and so this would be your slope. This would be your y-intercept. So this does fit the y equals mx plus b format. So this is going to be a linear function. When you graph it, it will be a straight line. Now, in all of our time writing equations, have you ever put an x in the denominator? Ever? No. And so this is going to be nonlinear because it does not fit the y equals mx plus b format. Oh, graphs. Hello. You just look at it. Is it a straight line? Not a straight line. This is not a straight line, so it's nonlinear. This is a gift. This is linear. Connect the dots. Connect the dots. La, 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 la. And then you have your continuous straight line here. This is linear. So great. Now, these two, whole different story. Much more difficult. Try to stay with me. I'm looking at this data table, and I'm seeing that the change in y here in this interval, say, of time, we're just going to say that just to make it make more sense. In this interval, this is dropping by, if we go from 12 to -3, that's a drop of 15 in, say, 3, I don't know, hours. Now, if this is linear, you're going to see, now what's that rate? That would be -15, over 3 would be a slope of -5. So that has to stay -5 every time you calculate the slope or the rate in order for this to say it has a constant rate of change. So let's check it. -3 to -15 is a -15 over 3. And so -15 divided by 3, -5. And then again, let's see, what is -18? How do you do this? How do you figure out? So I would just do, it's dropping. Just do 33 minus 18. And if it comes out, does it come out to be 15? You can't see my calculator. There it is, 15. So I know it dropped by 15. This was an easy one because you've got the same exact numbers coming up every time. So every single time it drops by 15, it's going up by 3. Boom, constant rate of change. This is linear. That is only the second time I've explained that to you, or third time. So no worries if it's not clicking yet. Let's try this one. In the y's, we went down by 1. In the x's, we went up by 5. So the slope is -1 over 5. And it should continue to stay -1/5 the entire time, every time you calculate it. Otherwise, it doesn't have that constant rate. So let's see right here. Oh, well, hello, already you can see. Going from 1 to 2/3. So this is going up by 5. Great. If this is going up by 5, this better be dropping by 1, and it is not. So it is changing its rate, or it's changing its slope. So this is going to be nonlinear. We will talk more about that. It seems to be one of the harder tasks in this unit. So we definitely need to talk about that a little bit more. But I'm glad that you're getting your practice time in now because it will help. The graph shows the temperature throughout the day in a city in California. Is the relationship shown linear? Why or why not? Well, this is nonlinear because it is not a continuous straight line. Again, I'm not writing the explanation because I'm trying to keep the video around 10 minutes. I'm a little bit over, but we'll get there. The table shows the height of a softball that Haley, I like the way she spells that, threw in the air. Is the relationship shown linear? Okay, so I can see this is going up by halves every time, and so what I should see is the same number over here as well. So this, from 0 and 5 and half a second, it went 7.2 yards. If this is linear, every half second, it will go another 7.2. And you can see right here, like I put in pencil so I didn't forget, it goes from 7.2 to 10.7, which is definitely not another 7.2 yards. This isn't like 3.5 yards. So as time goes on, you're gaining less distance. But at the end of the day, for you, you can see that between these 2 points, this is the slope, and between these 2 points, this is the slope or the rate. And because it's changing, it doesn't have what we say is a constant rate of change. It's not staying the same. So this is going to be nonlinear. And as far as 8th grade goes, once we determine that something's nonlinear, we're kind of done with it. You're going to be studying nonlinear functions more in 9th grade. And after today, you and I will delve into linear functions in a little bit more detail. Hang in there. I am so proud of you for doing the practice. Really, it makes a really big difference. I hope you can feel it in class when you have sat and really tried these on your own before getting to me, and it's making a big difference. So I hope you have a really great day, and I will see you soon.